First, I'll talk about some notions of tensor rank, and then I'll talk about the cap set problem. And then I'll talk about the connection between the two, and then I'll say some more about this new notion of p-stable rank and how it actually also helps with the cap set problem. Okay, so there are many notions of tensor rank. I'll just mention two notions that are relevant for this talk. So let's say we have a tensor product of D vector spaces. So this is maybe a work over a field F. And so the first notion, well, that's the tensor rank. I'm not going to define it, and actually I'm not really going to use it in my talk. There's another notion called the subrank. So what is the subrank? So if V is, say, an element of V, then the subrank, and maybe I'm just going to write sub Rk of V, is the smallest R such that there exist linear maps phi I from Vi to F to the power R, such that if we apply this tensor product phi 1 tensor phi 2 tensor phi d to V, then we get this tensor sum EI tensor EI tensor dot tensor EI. I is 1 to R. These EIs, these are the basis vectors of this R-dimensional vector space here. So and so the it's the largest. Sorry. Yeah. So that's the subrank. And the other notion of rank that I'm going to use is the slice rank. And this was sort of introduced by Terence Dow in his blog when he was kind of describing this proof of Ellenberg and Gijswijt, who proved this good balance for the cap set problem. So, so the slice rank say SLRK of V is the smallest R such that this is just my formulation. There exists subspaces Wi of Vi for I is 1 up to D, with V lies in W1 tensor V2. So you think of this sort of as a slice of the whole space V, and then here's sort of a second slice in the second mode of this tensor space, plus double dot plus V1 tensor double dot V D minus 1 tensor WD. And the sum of the dimensions of the WIs is equal to R. We kind of try to fit this V into these R slices. So now for DS2, the matrix rank is equal to the slice rank is equal to the subrank. And in general, we have that the subrank is less equal than the slice rank. And this is less equal than, I write here rank, but that's the tensor rank, okay, which I didn't define, and we don't really need for this talk. Okay, So these are the two notions that are important for this talk. And then that's the G-stable rank that I will introduce later. So let me now talk about the cap set problem. So this notation FQ is a field with pure elements. And the cap set is a subset S of F3 to the power n that doesn't contain an arithmetic progression. Or in this case, what is actually equivalent to an affine line. So in F3 to the power n, right, if you have 3 points, 3 distinct points, they're collinear, even only if they form an arithmetic progression. So and so the cap set problem is basically the question, how big can a cap set be, right? So let's define this function. Let Fn be the largest cardinality of a cap set. The cardinality, I'm going to use this notation here, of the cap set as an Fn to power n. So one observation is you can always take, S to be 0, 1 to the power n. That's a cap set. And so we see that Fn is at least to the power n. And actually, for small n, F1 is equal to 2, F2 is equal to 4, F3, you might expect 8, but it's actually 9. And F4 is actually 20. F4 is related to some card game called SAT. So that has some interesting recreational application. All right. Now there's a kind of a long history of finding upper and lower bounds. I'm not going to give a full history, but I'll mention some results. So there's a theorem of Edel that F and this is a lower bound, so 2.2174 to the power n. And as I was preparing for this talk, I noticed there's actually a preprint where somebody, Tyrell, actually proved slight improvements. So let me also mention that. 218 power n. Like 80 and then more digits, but no. And the result that I'm going to talk about is that I already mentioned Ellenberg and Gijswijt. And this was also partially inspired by this result of Crude, Love, and Koch, who gave some bound for cap sets in Z modulo 4 to the power n. But let me just say the statement of Gijswijt, Ellenberg and Gijswijt. So they proved Fn. Oh, sorry, I forgot one. So let me also mention there have been various upper bounds. So the first, the obvious upper bound is of course 3 to the power n, and then people have been slightly improving that. So for example, in 2012, I think, Bateman and Katz, they proved that Fn is O 3 to the power n over n to the power 1 plus epsilon for some epsilon. Before that, there was a bound of 3 to the power n over n. And, you know, there's a bound before that. But this new bound here is O theta to the power n, where theta is strictly smaller than 3. So it's like an exponential improvement. And this theta is roughly 2.7551, I think, something like that. And I can actually say exactly what it is. This theta is 1 plus gamma square over gamma to the power 2/3. But gamma itself is also an algebraic number. It's square root 33 minus 1 over 8. Okay, so that's what it is exactly. It actually comes from kind of trying to minimize this function. So if you take this function for positive x and you try to minimize, this is this value you get. And you know this is the x for which you have the minimal value. All right. So maybe also mention my student Zhi Jiang, who actually noted that you can actually improve this by factor square root n. And in fact, he actually proved something stronger, namely something like Fn is less equal than a constant times 1 plus small o 1 times theta to the power n for some explicit constant, some explicit c. So it's a little bit more explicit result. But yeah, this exponent, I don't know if we can improve this this theta here. It's actually, anyway, okay. So how does this relate to tensors? Well, it's kind of in the proof of Ellenberg and Gijswijt. But in this block of Karl, he described, and there are actually 2 blog posts that's sort of relevant, or at least 2, maybe more. And there's also one that he wrote together with Will Savin. And there he kind of introduced this notion of slice rank and used that sort of to give sort of an elegant exposition of the result of Ellenberg and Gijswijt. So I should mention these are pretty recent. Well, what is recent? Like 2000. Preprints are around like 2016. All right. So we're going to work with tensors, and the base field will be F3, maybe not surprisingly. But the vector spaces we consider, they're actually also going to be 3 to the power n dimensional. And we're going to use a basis of the space. We're going to label these basis elements also with elements that are in F3 to the power n. So maybe it can be confusing because the base elements are able with elements of F3 to the power n, and the coefficients also lie in F3. But yes?
You divide by square root of n.
Sorry? Oh yeah, thank you. So now consider the following tensor. Let's call it Vn. Sum A tensor B tensor C, where A plus B plus C is 0, So sorry. Sorry. Well, let me just say, of course, they lie in f3 to the power n, and the sum is equal to 0. When is the sum 0, right? So maybe I'll write. If you look at that, a plus b plus c is 0, if and only if. Well, if all three are equal, then clearly the sum is 0, because then it's just 3 times something and equals 3. Or a, b, c are on an affine line in f3 to the power n. So let phi from be the projection or okay, maybe I should say suppose S is a cap set. Let phi be the projection onto the span of all these basis vectors where A is an element of S. Then if you apply phi tensor phi to this tensor Vn, then what we get is, all these things are mapped to 0 except when A, B, and C are actually lie in S. Sorry, B, C. So as we see in a moment, that actually doesn't matter, right? But remember, so A plus B plus C means either they're all equal or A, B, and C lie on a line, but we know as is a cap set, so by definition it doesn't contain any lines. So this is just equal to some A tensor A tensor A in S. And so from that, if we look at the definition of subrank, exactly means, well, now instead of labeling from 1 to R, we labeled it with elements of S, right? But what we get is that S is less equal than the subrank of Vn is greater equal than the cardinality of S. Okay, so we have an upper bound for the cardinality, which is what we want. But then we have to know the subrank of this tensor that we wrote down here. And of course, we don't know what that is. Subrank is kind of not really an easy thing to work with sometimes. But we know that the subrank is less equal than the slice rank. And so we'll be able to say something about the slice rank. So now we're wondering if you can find an upper bound for the slice rank of this tensor Vn. So I need to introduce some more notation. So if f, and so this is sort of like, I guess, polynomial method, because now polynomials start appearing. If I have a polynomial in n variables, I'm going to use this notation, maybe f, with these brackets here, or this is going to be defined as the sum of all A in f3 to the power n, the value of f times this basis vector A. So I'm going to use that notation. And also if I have a polynomial in 3 variables, so if f a polynomial is the x1 up to xn, y1 up to yn, and z1 up to zn, then I'm going to use this notation. Then this is going to be sum of all a, b, c in f3 to power n, f a, b, c times a, and I'm going to use the standard product. Okay. And now we have actually a different description of this Vn. This Vn turns out this is exactly what you get if you use this function product I is 1 to n xi plus yi plus zi. Sorry, no, 1 minus. Product 1 minus this square I is 1 to n. If you look at this, if xi plus yi plus zi is non-zero, then the square is going to be 1. And then 1 minus 1 is going to be 0. And then this product is going to be 0. So this thing is only going to be non-zero if xi plus yi plus zi is equal to 0 for all I. Right? And that's exactly, and in that case, the value will be 1. So you get exactly this sum of all a, b, and c for which a plus b plus c is 0. And so now we're going to use a different basis, namely a basis of monomials. So f3 to power 3 to power n has basis. They're all monomials where m is a monomial with degree of m in the variable xi is less equal than 2 for all I. Now, as a function, xi cubed is the same as xi, so you can always get rid of powers that are more than 3 or more. And in fact, if you take all these monomials, you get exactly 3 to the power n monomials, and they form a basis. Every polynomial function can be expressed in this monomial basis. And basically every function is a polynomial function if you work with a finite field. So, all right. So Vn is a linear combination of all, right here, m1 in the x variables, m2 in the y variables, m3 in the z variables, which, is in our notation is the same as kind of the standard product of these 3 monomials. And we can say even more, because besides that, the degree, first of all, the degree of the mi in each variable xj, or maybe yj, anyway, is less equal than 2 for all I, j. But also the degree of m1, m2, m3 is less than equal than, if you look at here, this is a polynomial clearly of total degree at most 2n. Right, and this is just the degree of m1, degree of m2, plus the degree of m3. So if we take let's go back here. So that W1 is W2, W3 be the span of all monomials with the degree x, I, m less equal to 2 for all I, and the degree of m less equal than 2n/3, let's say round it down, then we see that Vn lies in W1 tensor V2 tensor V3 plus V1 tensor W2 tensor V3 plus V1 tensor V2 tensor W3, right? Because if the sum of the degrees, right, this is less equal than 2n, then one of these monomials has degree at most 2n/3. So every monomial that appears in Vn either lies in this space, in that space, or in that space. So we get this. And so we see that the slice rank of Vn is less of degree at most 2n/3, and for all I, degree xi of m less equal to 2. Okay. Now we have to do some combinatorics to actually count how many of these there are. But if you do that, then you get basically this Ellenberg and Gijswijt bound. I mean, you can improve it a little bit because sorry, yeah. Anyway.
Do we know how big can the gap be between the subrank and the slice rank?
Yeah, it can be quite large. So we know, for example, if you take sort of a random n by n by n tensor, it will have slice rank n, and the subrank will be roughly square root of 3n. So in some sense, we're looking kind of at asymptotic results here. I think in this, so I don't know. My feeling is that in this case, maybe they're actually closer to each other, the subrank, at least in the limit. But, I guess I don't really know. All right. So here's again the definition of slice rank. It shows you this. Okay. Well, let me now talk about the G-stable rank. And the various reasons, I guess, why I was studying this. But it, as we see, it also is related to the cap set problem. And it's actually also closely related to the slice rank, but not exactly equal. But the motivation comes kind of from geometric invariant theory. So G stands for like a group in, but let me just say some more generalities about, say, reductive groups. So let's say G is a reductive algebraic group over F, and let's say F is algebraically closed. And say V is a representation for G, finite dimensional representation. So then an element in V is called semi-stable. If you take the orbit, so this is the orbit with respect to this group, and then you take, say, this risky closure of the set. If that doesn't contain 0, then it's called semi-stable, and otherwise it's called unstable. So the other characterizations. So another characterization is that it's semi-stable if there's a homogeneous invariant polynomial that that's not constant, for which that doesn't vanish on V. So that homogeneous invariant will sort of separate the origin from the orbit. Now that F, so F star here, or F cross here, is just F without 0, right? This is the, you can also think of it as GL1, right? This is the multiplicative group. And that's this other notion in geometric invariant theory is, you know, the notion of a one parameter subgroup. So a one parameter subgroup is a homomorphism of algebraic groups maybe often called lambda from here to G. Technically, it's not really, you know, it may actually have a kernel, so technically it's not exactly a subgroup. But this is called the one parameter subgroup, or 1PSG for short. And so there's the following characterization of semi-stability, namely the Hilbert-Mumford criterion. V and V is unstable if and only if there exists a one parameter subgroup lambda with, and I'll put this in quotation marks, lambda t applied to V, if you take the limit t to 0 is equal to 0. Well, I put it in quotation mark because, well, if we don't work with the real complex numbers, we don't really have any topology, so limits don't really make sense. But we're talking about polynomials. So if you have a polynomial in t, then what is the limit t goes to 0? That's just the value at 0. Okay. So maybe be more precise, if AT is, say, a polynomial, or more generally, maybe it could be a vector of polynomials. Then we can write AT as a power of t times something that is non-zero at t0. Some polynomial or polynomial vectors. So then the t valuation of AT is S. Okay, so that's just a kind of definition. And so then you see that the t valuation is positive if and only if the limit sorry. No, let me check. So, well, let me just say, I think I already said this, but so this limit, right? This is by definition a of 0. And of course, this a0 is 0 if and only if the valuation is positive. So, so if you look at this valuation of t, of say lambda t times v, like if you go back to this, Hilbert-Mumford criterion, this valuation, so if it's positive, then this limit will be 0. But this valuation kind of tells you how fast it will go to 0. Okay. And that may say something about how unstable v is. Except that if I replace t by t squared, then of course this valuation is actually going to be multiplied by t. So it depends here. It kind of depends on the choice of this one parameter subgroup. Now we want to choose this one optimally, but of course if I choose t bigger and bigger, then I can make it go to 0 faster and faster. So we have to kind of measure it relative to something else. And that's sort of where this idea of the G-stable rank comes from. So in our situation, we're going to take G to be a very special group. Right? We take this group, just the product of GLs. And this group X on V, which is the tensor product. Okay, so we're wondering about stability inside this tensor product space. Now I need to introduce one more thing. So lambda, so a one parameter subgroup. Let me just abbreviate that. Of G is of the form, well, it's just really an n, a D tuple of one parameter subgroups. Okay, so that's how one parameter subgroups of G look like. And I say that lambda is polynomial if may I write like this, if lambda I t is a matrix with polynomials. For all I. So how do one parameter subgroups look like? Like for GL, it could be, a diagonal matrix where you have, on the diagonal, you have powers of t. That's sort of a typical. Such a matrix would be one parameter subgroup, and you can also conjugate it with some constant matrix, and you get another one parameter subgroup. In fact, this is how all of them look like. But these exponents a priori can be any integers, but for it to be polynomial, then they all have to be non-negative integers. And so now we can define Well, first of all, if lambda t is a polynomial one-parameter subgroup of G, and limit of lambda t v is equal to 0, which really means, right, that this evaluation, t-evaluation of lambda tv, this is a positive number. Well, I'm going to look at this quantity. And this we call kind of the slope mu lambda t comma v. You can think of this as some kind of slope with respect to this one-parameter subgroup lambda t and this v. Okay, and so this is kind of a measure of how fast lambda t goes to v, because if I now replace t by t squared, then I also replace t by t squared here. So then this might be multiplied by 2, but the numerator is also multiplied by 2. So this reparameterization will not affect this slope here. And so now we can kind of look for the optimal slope. So the G-stable rank of V is the smallest possible slope mu lambda t v all, lambda one polynomial one parameter subgroup of G with t evaluation of lambda t v positive. So that's the definition of G-stable rank. It's somewhat complicated, but it's sort of a natural thing if you're interested in, I guess, geometric invariant theory and kind of measuring, one parameter subgroups.
So in priori, this is an infimum, right? But it is an infimum.
Yeah, you're right. A priori, it's an infimum. Yeah.
It agrees with matrix rank.
Yes, it does agree with matrix rank. So if, for example, if I had a matrix of rank 2, maybe like this, and then the rest all zeros, then I could multiply here on the rows. I could multiply by t, 1, 1, etc. So that gives you kind of one parameter subgroup. So this lambda 1t would be sort of t and then ones. And the same actually for lambda 2t. And if you multiply this row with t and this column with t, then everything is multiplied by t. So this denominator would be 1. And then the determinant would be t, and so here would be 1 plus 1. And then that would be sort of the optimal one parameter subgroup. In fact, yeah, let me do kind of a similar example. And so a priori, this is a quotient of two integers, positive integers. So it doesn't have to, the slope doesn't have to be an integer. And in fact, it's not. And the minimum, well, if it's a minimum, it would be a rational number. If it's an infinite, it could even be a real number. But in fact, it is a minimum. So, but anyway, let's look at the following example. V is E2 tensor E1 tensor E1 plus E1 tensor E2 tensor E1 plus E1 tensor E1 tensor E2. Then again, you could take kind of similar situation as the other example here. Take these all to be, this matrix T001. And so you multiply each E1 by T. So you see that lambda T V is T square V. Usually there might be higher order terms, but in this case, it's just exactly T squared times V. And we see that the slope lambda T is, well, this determinant is T, so you get 1 plus 1 plus 1. And now here we get actually T squared here, because each has like 2 E1s in them. And so we get 1 plus 1 plus 1, get 3 over 2. And it turns out, so that means that the G-stable rank of this tensor is less than equal than 3 over 2. And in fact, it's equal. So this is, I don't know if you like it or not, but the G-stable rank is a rational number. Okay, it's not always an integer.
Are there 3 tensors that have G-stable rank strictly between 1 and 3 over 2?
No, I don't think so. The 3 over 2 is the smallest. That's bigger than 1. Right? Because we know actually we have to have the following things. The subrank is still less or equal than the G-stable rank. And this is less or equal than the slice rank. And in fact, it turns out it's not too far away from the slice rank, because it's also greater or equal than 2 over D times the slice rank. So here in this example, the slice rank of V is equal to 2. And well, the rank of V is, the tensor rank is actually 3, but and then there's also border rank, which is 2, but and the subrank is 1. And but 2/3, if I multiply this with 2/3, I get 4/3, which is more than 3 over 2. All right. So in principle, we could do this whole story about CAPTCHA problem, but instead of using the slice rank, we could use the G-stable rank, and well, we could just slightly improve the bound, right? It's not going to be drastic improvement, because the slice rank and G-stable rank only differ by constant. So if you only care about, but in this version of Zhi Jiang's version, where there actually was an explicit constant, then it would matter, like which notion you would use. And also from a general perspective, this G-stable rank has some nice properties that the slice rank doesn't have, which may or may not be useful for the CAPTCHA problem, but in any case, it's an interesting notion. Let's see. Yeah, let me. What time exactly should I stop, by the way? To go up into the hour?
We still have 5 minutes or 5 minutes.
Yeah. So maybe I'll first say, mention some other nice properties. Yeah, so first of all, for for small values of n, you can get using the G-stable rank, you can get better bounds than using the slice rank. But then there are also kind of other tricks that one could do, which is not necessarily exactly using the slice rank, but like if on the Taoist blog, there were some discussions between Petrov and Tao, where they kind of improve some various tricks where you can kind of improve the concept a little bit better. So, but that's not necessarily changing the definition of slice rank, but kind of using more careful analysis and kind of going a little bit away from that definition. But anyway. Let me just mention some other properties of G-stable rank that I think are interesting. So it behaves well with sort of adding and tensoring tensors. So let's say we have V V1 up to Vn. And another tensor that's in another tensor product. Then we can kind of take the direct sum, which is a tensor in V1 plus W1 tensor. Oh, sorry, this is D. VD plus WD. And you can also sort of take this tensor product, but we view it inside the tensor instead of thinking of it as something in the tensor product of 2D spaces. We think of it as a tensor product in something of D spaces where I pair the VI's and WI's. So sometimes I use kind of this other notion, and this is sort of like a Kronecker tensor product. Well, you know, if like this is called like a tensor product of two matrices that gives you like a big matrix, you can do that also for tensors. So that's why I sometimes use a different notation rather than this notation, because I just view it in it as a different structure. And so what happens to the G-stable rank? Now, if you have it, it's sort of nicely additive with respect to Derksen. Maybe that's not so surprising. And in fact, I didn't say this before, but like most notions of rank, it satisfies the triangular inequality. Now, the tensor rank actually has this triangular inequality, but the tensor rank doesn't have this additive property. Right, that's a counterexample that I should have. And then another nice property is for the tensor or Kronecker tensor product. Now, well, nice would be if it were exactly equal to the product, but it's actually super multiplicative. It's maybe surprising, I don't know. I found maybe expected to be sub-multiplicative, but it's actually super multiplicative. So I'm not sure. I think in this example, if you take the V Kronecker tensor product with itself, I think the rank may be like 3. But anyway, I'm pretty sure it's more than 9/4. So it's this property. Now, the slice rank, for example, is not super multiplicative, nor is it sub-multiplicative. It's neither. So in that sense, and maybe the last thing, looks like time's up. The last thing I mentioned maybe is if you work with the complex numbers. Because all that I've said so far, it's usually easy to find an upper bound for a slice rank. In any case, right, to get an upper bound, you just need some explicit one parameter subgroup, and then you can easily compute something, and will be upper bound, right? Because it's the minimum of these slopes. If you just know one slope, you have an upper bound. It's kind of hard to find any like lower bounds in general, right? And in fact, in characteristic 0, at least, we can also get, there are also ways of finding lower bounds explicitly. So if, let's just say F and C, another thing is, for example, the dependence on the field. So if you go to like a finite field extension, then the G-stable rank doesn't change, which is kind of a nice property. So let phi IV be the ith flattening. And what is that? It's basically the same as V, but now we think of it as a matrix. Or yeah, you think of it as a matrix. So you group all the vector spaces together except one. And so and then you think of it as sort of a matrix. Then it turns out that the G-stable rank for V is the maximum of all G in the group, which is the product of the GLs, taking the minimum of all I from 1 to D, where here, this is, you apply this group element to V, and you take the Euclidean norm. So in fact, you have to choose some, well, these should be some Hilbert spaces. And then you view the same thing here, but as a matrix for every I, and you take the spectral norm. So this here is the spectral norm or operator norm of a matrix. And so since this is a maximum, right? If you find any G and you compute these norms, which is easy to do, then you have a lower bound for the G-stable rank. So maybe in this one example, maybe we can do that here. Oh, maybe we can. Let me just do it here. So what can we do? So these flattenings. Well, first of all, this tensor looks like this. So think of it as a tensor of two slices, where each slice is a matrix. One slice is this matrix, and the other slice is this matrix. And so the flattening is basically this 2x4 matrix. It's one of the flattenings. You could do some orthogonal transformations, and this sort of equivalent. Well, maybe right like this. So this matrix, these are the flattenings look exactly like this. And you see the singular values are 1 and square root 2. So the operator norm of V is exactly square root 2, which is the largest single value. And so you see that the max, may write here phi I. And so you get here, minimum of all I, and here you get square root 2 square. And here the Euclidean norm square is 3. So you get this here. And so this is a lower bound for G-stable rank, which is 3/2. So in that case, that would prove that it's exactly equal to 3/2. But it's actually also true for an arbitrary field for this simple example. Okay, I stop here. Sorry.
Any questions?
Can this like rank approach, could it work to show that a subset of like fp to the n for some p doesn't have a subspace of dimension 2? Like that upper bounding is set like that.
Can you say again? So you say fp to the power n?
Yeah, for some p.
Yeah. You mean the same problem for?
Yeah, the same problem, except you replace like a linear subspace with a two-dimensional subspace.
Oh. I have to think about, like, if you do the same problem with arithmetic progressions, right? Then the same construction works, right? In fact, Ellenberg and Gijswijt also had some result for arbitrary, subsets that don't have arithmetic progressions and have q to the power n, and so you could, that works.
It's free term.
Right?
3 term.
Yeah, sorry, yeah, 3-term arithmetic progressions. So I think subspaces, yeah, probably would be hard, or yeah, it might be hard because we don't really know how to go. For example, to go from no arithmetic progressions of length 3 to larger length. So we don't get any good results for that yet. Probably need some new ideas for longer arithmetic sequences. So I suspect for subspaces, probably also different. Yeah.
You could just define rank for a tuple of matrices too, the same way.
Yes. So one thing I didn't mention is you could also define G-stable rank with respect to slope. So you got to put here some parameters here, and you could also do that for slice rank. So then you get some kind of G-stable rank with respect to a slope. And if you take one of these alpha i's equal to 0, then you can think of that as sort of you have a tuple of tensors. And so I think you may be able to formulate the non-commutative rank this way, where one of the alpha i's is equal to 0. Yeah.
So if there is no more question, let's thank the speaker again.